All right, moving on. Third part of this module, we have the scalars and vectors. So scalar quantities are fully described by a magnitude or numerical value alone. Okay, when we are measuring things, we sometimes we have to be aware whether we are measuring a scalar quantity or a vector quantity, because aside from their magnitude, we there's another thing that matters. Okay, that if we disregard could lead to wrong measurements or could lead to some errors in our measurements. Okay, so we have such thing as vector quantities, which are fully described by both a magnitude and a direction. Okay, so we have some examples here of scalar and vector quantities, and among the most basic and important examples are the distance and displacement. So, they are very much similar, but there's a thin line that divides them, and that thin line could actually lead to a very big um, difference eventually. So, as you can see, distance is a scalar quantity that refers to how much ground an object has covered during its motion. So, no matter the direction, no matter if the person goes back and forth, left or right, up and down, or whether it stopped for a while and then continued, carried on, and so on, distance is still measured on how much it has traveled. Okay, so for example, here, if the person um starts at this point, at the start, uh, the word, at the word start, okay, and goes through this direction. It's a curvy direction and leads to a very near place, uh, very not so far from its initial position. Then the total distance it covered is actually the distance, okay? But how far it is from its initial point or start point is now called a displacement, okay? So displacement is a vector quantity describing how far out of place an object is, meaning how far has it changed from its initial position, okay? How much change from between the initial and the final positions, right? So displacement is the object's overall change in position, right? Another example, a simpler one, as you can see, from this tree and up to this house, as you can see, if you go to this through this path, okay, if you're um if this is the only road, then you are actually this your distance would be this one. Okay, you travel 4 meters to the right and then 3 meters to upward. Okay. But if you can simply fly from your initial point up to your target destination, then your distance could be this short only. Okay. Um that's why displacement is also somewhat um related to what military people call the air distance. Okay, so somewhat like distance only is the ground distance for the military people, while displacement is the air distance. So imagine if you're riding a plane, there's no need for you to go through this path. Okay? You can simply go straight from one point to another. Same thing here for the curvy path. The plane does not need to follow this path. The plane can simply go from the starting point directly to the end point. Okay, so imagine displacement as somewhat like a moving plane. Okay, imagine what path would the plane would take. Okay, if it has to travel from point A to point B. So Normally, that's the direct path. Okay, and that's the displacement. So, um, remember, distance, a zero distance would mean the object did not travel at all. Okay, there's no travel that has taken place. Okay, but when we say zero displacement, that's not always the case. It could mean the person, or I mean, the object traveled at some point in time, and then finally it went back to its original position. Okay? So no matter how far that object traveled, the displacement is still zero if it went back to its original position. Okay? I hope you get the point. You get the difference between the two. Okay? And we have other terms, we have other common physical quantities that are defined as either a scalar or velocity. Okay, so in once we have the distance, we can actually um get also the time or measure the time so that we can derive the speed. Okay, if we say speed, we are basically referring to a scalar quantity only. Okay, that's the rate of change of distance. Okay, there's no direction involved. Okay. On the other hand, when we say velocity, that's already a vector quantity that is defined as the rate of change of displacement. So that means it's no longer just magnitude. There's a direction that is involved. Okay. So when we say 5 meters per second, that's only speed. We doesn't matter which direction it goes when we say speed. But when we say velocity, 5 meters per second to the west, to the west, is not the same with the 5 meters per second to the east, or even to the north, or to the south. Okay? So velocity is more specific, right? Um, Also, if we go farther, if we take the rate of change of our velocity, then we come up with our acceleration. So it's also a vector quantity that actually refers to the rate of change of the velocity of an object with respect to time. Okay, same thing with the speed and velocity. Rate of change of distance or displacement with respect to time. As you can see in the formula, the distance over time, displacement over time. Okay, so the orientation of acceleration is given by the orientation of the net force acting on the object. So force is another vector quantity, which we will be discussing in the one of the next modules. Okay, we're going to discuss or to talk more about force in those modules, right? Um, okay, kindly observe this graph. Also this image. What I want to introduce right now is actually the concept of this is where the calculus takes place or starts to creep in in our physics, in our study of physics, right? So um if you have noticed, we can actually say that speed is the derivative of distance with respect to time, or to be more exact, velocity, because velocity is more specific. Velocity could actually be defined as the rate of change of your displacement, meaning how much displacement changes over time. So you can actually use calculus to better represent your velocity. Okay. So in short, it is the derivative. Velocity is the derivative um of your displacement. Or in other words, um conversely, distance, or I mean displacement, is the integral of your or the antiderivative of your velocity. Okay. So from velocity from okay. So before I go too technical, too deep, okay, just observe this. All right. So okay, position is actually the double integral of your acceleration. So meaning if you take the derivative of your position, okay, this normally the acceleration has a curved or like a quadratic function, okay, quadratic graph. Okay, so if you take the derivative of it, then you get the slope of this curve. Okay, so from double integral, it now becomes single integral. Okay, so normally from quadratic, you come up with a linear equation. Okay, so um, remember acceleration usually uh, occurs in a quadratic uh, um, trajectory or no um, form. Okay, quadratic form, while velocity is usually in a linear form. But ay no no no. I was referring to position earlier. Position is normally in a quadratic form, and if we take its derivative, we get the velocity. So from double um if the position is double integral of your acceleration, the velocity is single integral only because the other integral sign has been cancelled out when you did the when you took the derivative. Okay, so again, position. Okay, we have normally have this graph, and then if we take the velocity, we are taking the derivative of it. So now it only has this formula. Okay, and if you take the derivative of your velocity, you get your acceleration. So the derivative of this is just a. Okay. So, but if you go to the right from acceleration to velocity to position, then you are actually doing integration, okay, or taking the antiderivatives. Okay. And again, derivative of position is velocity. Derivative of the velocity is acceleration. I hope you got it. Right. So now, moving on with vectors, we have such thing as vector components, which allow physicists to break a single vector quantity to two or more scalar quantities, with which we have more mathematical experience. And the process of breaking a vector into its components is called resolving into components. So for example, if we have a vector, this velocity, we have 25 meters per second, we can analyze it by breaking it down into its components. So we have the x and the y components, and actually you can do that using trigonometry. Okay, you can do that using your SOHCAHTOA. Okay, so um as you can see, we have the angle 27 degrees. So to take the um the what do you call this, the opposite side. Remember, this is opposite. So sine is opposite over hypotenuse. So opposite, this one, the Vy, over hypotenuse. So sine 27 is Vy over 25. And we can reverse that. We can manipulate that so that Vy is equal to the hypotenuse times the angle, the sine of the angle. Okay? So I wish I could write it here. But just remember, this is based on SOHCAHTOA only. So sine of 27 degrees is equals to Vy over 25 meters per second. While the cosine, remember cosine is adjacent over hypotenuse. The cosine of 27 degrees is Vx, the adjacent side, Vx over the hypotenuse. So that's a simple way of breaking the components. We basically take the sine and cosine of the angle and multiply it with the hypotenuse or our vector. So if you can't get it, just remember that the vertical component is the sine of this angle, while the horizontal component is the sine um, of this angle, and they are both multiplied by your vector's magnitude. Okay, so when you see this and this angle is with respect to the x-axis, just multiply this number by the sine of this number of this angle to get the vertical because sine vertical. And to get the horizontal component, just multiply this number by the cosine to get the horizontal. Okay, so just remember vertical sine, horizontal cosine, and that is if the angle that we are talking about is with respect to the x-axis. Okay. There are times that we have the vectors like this. We have this vector and this vector, the another vector, and we want to know what's the overall value of that or the combination of those vectors, or should we say the addition of those vectors. Okay, remember that vector addition is not the same with scalar addition. The addition process that we know is actually more of scalar only. Okay, wherein we directly add two or more numbers. In vector addition, we are actually doing something like Pythagorean. So if you want to add this vector to this vector, then you just use this formula, the Pythagorean formula, to get what we call the resultant or the overall vector. So resultant is the vector quantity that is equivalent to the combined effect of two or more component vectors acting at the same point. So, okay, for example, this one, okay, using our knowledge in trigonometry and our basic knowledge in vectors, we can actually determine what's the overall vector quantity that that acts on this specific point. Okay, and that specific point will be discussed further in our next module. Actually, okay, we're going to talk more about vectors and what we call centroids. Right? So remember, these are different vectors and they are acting on this specific point. Okay, so we're going to learn more of that in the next module. In the meantime, remember that we are dealing with calculus-based vectors. So I already mentioned this previously. This is just to give you some more illustration. Okay, so you just it's meant for you to observe. Okay, as stated here, an object's position vector r of t traces a path through space, and its velocity v of t is the time derivative of the position. Okay, so as you can see, the formula, if our position is r of t, then the velocity is just the derivative of it with respect to time. Okay, and pointing tangent to the trajectory and indicating instantaneous direction of motion, just like what you see here in the graph. And the object's acceleration a of t is derived or is the derivative of velocity. So it's here. A of t is just the derivative of the velocity. And we know that the velocity is the derivative of the position. So therefore, we can also say acceleration is just the second derivative of the position. Okay. It captures how speed and direction change. Okay. And conversely, you can see that the two are can be reversed. Okay. So for example, position is just the Okay, just explore that because we don't have time anymore. Um, okay, so just observe the relationship between the three. And later on, we're going to see more in the next modules, you're going to see more of calculus in physics.